In this video, I'd like to discuss measures of frequency as they are commonly used in epidemiology. The whole idea of thinking about populations as an entity derived in the mid-17th century. That was the time that the field of demography started developing, and one realized that knowledge about the population was important to regulate growth. There were two pioneers of population thinking to note. The first is William Farr, who worked at the General Registry in the United Kingdom. He realized that information on demography was beneficial for public health. He continued to stress the importance of denominator data. The second was John Grant. He compiled all deaths and births in UK parishes. And by doing so, he was able to publish the now famous book Bills of Mortality. And in that book, there was an endless listing of all kinds of causes of death that were encountered in the parishes. And there were some great names attached to it. So, for example, Mother, Riving of the Lights, or Skitch. This population thinking led to combining the frequency of disease occurrences together with information on population denominators, and as such saw the formulation of what we call now the epidemiological fraction. And as we mentioned, counting occurrences of health events is the core business of epidemiology. So the epidemiological fraction is a formula that relates the number of occurrences in the numerator in red with the denominator from which these occurrences occur in the denominator in blue. And how we express the epidemiological fraction depends on what type of data we have in hand and on what type of occurrences we are interested in. Are we thinking about new cases only or about any cases in a certain time frame? Or, for example, do we want to know the epidemiological fraction at a certain point in time in a cross-sectional fashion, or are we much more interested in the epidemiological fraction in a study that has some time of follow-up? In this picture, I denote the occurrences of health events of 10 individuals. The squares in blue indicate when a person is ill or remains ill. So in a cross-sectional way, we ask ourselves how many people were diseased or were having the occurrence of interest at month 3, for example, or at month 22. And when we have this cross-sectional approach, we actually calculate what we call the point prevalence, which is the total number of events at a specific time point in the population that was available at that time point. Now take a moment to answer the question what the point prevalence was at month 3. At month 3 there were 2 people who were diseased, this one and this one, out of 10 individuals available. So that is 2 out of 10, which is 20%. And in the same way we can do it at month 22, where there was only 1 person diseased, which makes it 1 out of 10 is 10%. Related to that, we could also ask ourselves how many people have been ill between month 3 and month 22. So we are not focusing on just one time period, but we denote a certain time frame. And by doing so, we are calculating what we call the period prevalence. So that is the total number of events in a specific period in the total number of individuals that were available in that period. So again, take some time to calculate the period prevalence of disease between month 3 and month 22. In this example, that was actually 10 out of 10. All the blue squares occurred in the period between 3 and 22 months. So the period prevalence was 100%. Now take a longitudinal approach, so where we have a cohort of people that we follow up over time. And this graph is now slightly different. The blue lines indicate the follow-up of time of each individual, while the zeros and the axes denote either the absence of disease or the presence of disease at the time that it was established. So if we want to know the epidemiological fraction at the end of follow-up, we would count the new events that were occurring during follow-up and the number of people who were at risk at the start of follow-up. Such an epidemiological fraction is called the incidence risk, or in other terms, the cumulative incidence. It is the total number of new events during the follow-up in the populations that were at risk at the start of follow-up. So try to calculate the cumulative incidence or the incidence risk in this picture that denotes the follow-up of 10 individuals that were all assessed for the absence or presence of disease at month 24. The incidence risk or the cumulative incidence in this example would be 6 out of 10. At the end of follow-up, there are 6 individuals who were having the disease during their follow-up. The previous example had the perfect situation where all individuals who started the follow-up also ended the follow-up. There was no loss of information, and therefore could calculate what was happening after 24 months of time. But much more often we have to deal with situations where persons start their follow-up, but some of them never reach the end of the follow-up. So the assessment of their absence or presence of disease is made somewhere during the follow-up. For our measure of frequency, we now have to take into account that not every person is follow-up. So we are still interested in the new number of occurrences during the follow-up in those people who started the follow-up. But instead of an incidence risk, we now calculate an incidence rate, or in other words, an incidence density. The numerator is the same, the total number of new events during follow-up, but the denominator differs. It's now the total number of follow-up time for all the patients who started to be at risk. So the difference between a risk and a rate is that a risk has as denominator the total population, while a rate has as denominator the total follow-up time generated by the population. In this example, there are still 6 occurrences of the event during follow-up, but they are accrued during 162 months of person follow-up, which makes it 0.037 event per person month, or we can translate that into 0.44 per person year, or 44 per 100 person year. The way that you express the incidence density does not really make a difference. We often do it in such a way that it has an easy way of expressing. 44 per 100 person year is a much easier way to express than 0.44 per person year. So then what are we going to do when there is not only attrition in our cohort, so there are people lost to follow-up, but also people entered the follow-up at completely different stages, as denoted here. There are some people who are in follow-up right from the start, or there are people who enter the cohort much later. Well, actually, we do exactly the same. We are still interested in the number of new events during follow-up, and at risk are those people who were in follow-up. So we still calculate the incidence rate or the incidence density. So we still look at the total number of new events during follow-up that were gathered in the total follow-up time in the population at risk. Only when there is also staggered entry and attrition, the number of person time accrued, so the number of months that people were really into follow-up, differs. So if we look at this graph, there are still 6 events, but instead of 162, there were now just 126 months of follow-up because some of the people were not in a follow-up right from the start. And that would make 0.048 per person month or 0.58 per person year. And as said earlier, we can express it in such a way that it is a bit easier. We make it 58 events per 100 person years of follow-up. So in the examples, we actually have seen 3 different kinds of populations. The first population here is actually a typical example of a closed cohort. You start at follow-up and you end up follow-up and there is no loss to follow-up. The other 2 populations are examples of a so-called dynamic population. People are lost to follow-up and here people come and go into the dynamic cohort. So what type of measure of frequency can we use in these populations? We can always calculate prevalence. We can always say how many people are diseased or are having the outcome at a certain point of time, even if that certain point in time is part of a much larger follow-up. The question whether that makes sense is something else. Because if you have follow-up, it is much better to have a frequency of occurrence that is expressed as an incidence. And that incidence is either a cumulative incidence when we have a closed population, so there's no loss to follow-up, or we calculate it as an incidence density, as a rate. So that deals with either attrition and or late and staggered entry into our population. So we have discussed both prevalence and incidence, and clearly there is a relationship between incidence and prevalence. And the way to describe this is often used by the bathtub or the coffee machine, whichever visual explanation you want. So here we have the faucet. From the faucet there is a continuous entry of water into the bathtub, and in the bathtub the water accumulates. And unfortunately there's also a leak in the bathtub, so some water is also lost from the bathtub. The water entering the bathtub can be seen as the incidence. The water present in the bathtub can be seen as prevalence, and the prevalence is decreased when people are lost to follow-up, which we cannot assess, which in epidemiology is often due to loss to follow-up, but also to death or to recovery. If you're ill and you recover, then you're not ill anymore. You have been an incident case, you have been a prevalent case, but a little bit later, when you're recovered, you're not a prevalent case anymore. So the relationship between incidence and prevalence is actually through the duration of disease. If the duration of disease is very long, the prevalence will increase when the incidence increases. Because water is getting into the bathtub, but because the duration of the disease is long, there is no loss of water, or at least very little loss of water. So the water level would easily rise. If you have the same incidence, but a disease is cured very, very quickly, then the water will not rise that fast because a lot of water is removed from the bathtub. The relationship between incidence and prevalence through the duration of disease is mainly conceptual, because this mathematical relationship only holds when there are some very firm assumptions met and which are very unlikely to be met. The population size cannot differ, there is no migration, and either somebody is at risk for the disease or has the disease. In real life, it is very unlikely that all these three assumptions hold at the same time. However, it is still a very useful concept because it is actually used in public health. Because the whole idea of diagnosing people and treating people is really a way to reduce prevalence, to reduce the burden of disease. Now let us look at mortality. Mortality is of course also a health event, and you can express mortality as the incidence of death. And mortality is often specified within a certain time frame, so the mortality risk in 1 year or in 10 years, or it is often expressed as population, the mortality risk per 100,000 population. Mortality is very often used as a health indicator. For example, to see how healthy a nation is, one could look at the infant mortality rate or the under 5 mortality rate. Another would be the maternal mortality rate. So death is a very important indicator for health. But it is also a very difficult indicator because how many people die within a population clearly depends on how that population is formed. What is the age structure of that population? What is the sex structure of that population? Because a population that is very, very young will have a clearly different death mortality rate compared to a population that is very, very old. So as soon as we start of mortality, we want to adjust for differences in age structure. And one way of doing that is to standardize mortality. So we standardize the frequency of occurrence when we talk about mortality. And as I said, because the crude mortality rates in a certain population are very difficult to compare. We do that by using a standardized population. And either we can directly standardize the mortality rates or we can indirectly standardize the mortality rates. So let us look at direct standardization of the mortality. Assume we have a population 1, that is 10,000 inhabitants large, where we have some young people, some middle-aged people, and some elderly people. And assume that we know the mortality rate, so 1% of the young die within a year, 0.5% of the middle-aged persons die within a year, and 2% of the old persons die in a year. That would give us 39 deaths in 1 year in the young population, 22 in the middle, and 32 in the elderly population. And altogether, that would make 930 per 100,000 per year. Now let's assume that we have another population, population 2. Also 10,000 people in that population, but the differentiation between young, middle and old is slightly different. However, the risk of dying is exactly the same as in population 1. But the number of deaths that we now expect is 134, or in other words 1,340 per 100,000 population per year. So although the risk of dying is exactly the same as in population 1 and population 2, the number of deaths that I see is different. And the main reason for that is because the age structure is different, with a few elderly people in population 1 and much more elderly persons in population 2. Therefore, comparison of the crude mortality rates of 930 and 1340 do not show the underlying identical risk of dying in the populations. To be able to compare these populations, we need some kind of benchmark, and that benchmark we call the standard population. And we can use anything like a standard population, completely fictitious, or another country, or the world population, whatever you want, as long as it is a well-defined population. An easy way to get a standard population is just to add the population numbers of the two populations that you want to compare. And that is what I did here. So I added this 3,900 young together with the 1,900 young in population 2 to come together with 5,800 young people in the standard population. And I did that for all three. And by adding them, of course, now I have a standard population of 2 times 10,000 is 20,000. Direct standardization means that I use the mortality risk of the population, of one of the populations that I want to compare, and project that mortality risk on the standard population. And if I do that, if I project this mortality risk of population 1 on the standard population, I will come to 228 deaths, or in other words, 1,140 per 100,000 per year. So what would happen if I project now the risk of dying, the mortality risk of population 2 on the standard population? Well, I will get exactly the same number of the standardized mortality. Why? Because now I do capture that the risk of dying in population 1 and population 2 are exactly the same. So if I project the same risks on the same standard population, I will come to the same answer. Indirect standardization is actually the other way around. We have a standard population of which we know the age-specific rates for dying, and those rates of the standard population we then project on population 1 and population 2, which have most likely a different age structure. And we very often do that when the age-specific rates in the populations that we want to compare are not available. I will explain the indirect standardization in another video. So to conclude, epidemiology refers, as said many times before, to measuring the occurrence of health events within the population. And to do that, we need to express it as an epidemiological fracture. The way how we express this epidemiological fracture depends by which type of event we look at and which type of population we look at. But the numerator will always be an indicator of the occurrences, and the denominator will always be an indicator of how many people were at risk. Mortality is a very special incidence and requires often standardization so that we are able to compare different groups. And the reason for that is that mortality is highly associated with the age structure of the population, which are most likely not identical when you compare populations. Only by standardization you can compare mortality between